Hi everybody, welcome back to this course on internet technologies. I am Vardan and today we'll be studying about authentication and cryptographic hash. When we talk about authentication in a networking or cryptographic context, we don't mean passwords. Here, authentication means confirming the genuineness of a message that it's not been tampered with, and more importantly that it's actually from one who claims to be. Now, an important point here is that authentication doesn't necessarily require any encryption. While encryption hides the message content, authentication ensures message integrity and sender authenticity. These are two different goals, though they can work together. There are three main ways to achieve authentication. First is using a symmetric key encryption. You can encrypt the message using a shared key, and the ability to decrypt it proves authenticity. Then using an authentication tag. So no encryption is required. You just add a verification tag that proves that the sender has access to the right key. Finally, using a message authentication code or MAC, which is essentially a cryptographic tag generated from the message and the key. We'll now dive deep into each of these methods. Let's first look at how we can use symmetric encryption for authentication. Here's how it works. The sender and receiver both share a secret key K. The sender encrypts the message M using that key, producing the ciphertext C. This is sent over the network. When the receiver gets C, they decrypt it using the same key K. If the decryption gives a meaningful and expected message, it proves two things. The message was not tampered with, and only someone with the correct key could have sent it, which authenticates the sender. So, in this method, symmetric encryption achieves both confidentiality and authentication. However, encryption is computationally more expensive than what we may need, especially if we are only worried about verifying message integrity and source. That's where the next method comes in. Now, sometimes we don't care if the message is visible. We just want to be sure that it has not been tampered with and it came from the right sender. In such cases, encrypting the whole message is a bit of an overkill. Instead, we use a lightweight technique. The sender computes an auth tag, which is a short piece of data derived from the message and a secret key. This tag is sent alongside the plain message. When the receiver gets both, they compute the expected tag themselves and check if it matches the one they received. If it does, the message is considered authentic. This approach keeps the data transparent while still ensuring integrity and authenticity. The actual algorithms for generating these tags are what we'll explore in the next slides, starting with the MACs. The message authentication code or MAC is a standard cryptographic technique used for verifying the authenticity of a message. It works as follows. The sender and receiver share a secret key K. When the sender wants to transmit a message M, they compute a tag, the MAC, by passing M and K through a secure cryptographic function. This tag is usually a fixed length output like 128 or 256 bits, regardless of how big the M is. The message is sent without encryption, but the MAC is attached. So M plus MAC. When the receiver gets this, they compute the MAC again using their copy of the secret key and the message that they received. If the MAC they computed matches the one that was sent to them, the message is considered authentic and unaltered. Now, MACs are very fast, efficient, and they don't expose the key, but their security entirely depends on the secrecy of the key and the strength of the hash or the block cipher used to generate the tag. So, I believe this is the right time to understand a very important concept that forms the foundation of modern authentication, the hash function. A hash function takes any amount of input, it could be a short sentence or an entire encyclopedia, and converts it into a fixed length output called a hash value or digest. This is usually a short string of bits like 256 bits for SHA-256. The magic of good hash function is that even the tiniest change in the input, like changing a single comma, will completely change the output hash. This is known as the avalanche effect. For example, imagine if you take a 500-page book and compute its SHA-256 hash, you get a neat 256-bit output. If you then change just one character in the book, say add a period, and the entire hash becomes completely different. Another important thing is that hashing is one way. You can easily calculate the hash for some data, but you cannot reverse it to get the original message. That's what makes it useful for authenticating data, but not for encrypting it. Hashing is fast, consistent, and deterministic, meaning that same input will always yield same output. And this is what we now use in cryptographic way to build max and authentication systems. Before we talk about the different hash algorithms, there's one important term we need to understand, which is collision. A collision happens when two different messages produce the same hash value. Since hash functions are supposed to give a unique fingerprint for any given input, a collision is a serious problem. It means the hash function can't be trusted to guarantee integrity. For example, if an attacker can generate a fake document that results in the same hash as a trusted one, they can pass it off as genuine. That completely breaks the authentication. So, there are two major families of cryptographic hash functions, these which are commonly mentioned, and one is the MD family and the other is the SHA family. The MD family includes MD2, MD4, and MD5. These were once widely used but are now considered very insecure, especially the MD5. It was fast and popular, but researchers discovered how to generate collisions, which made it unsafe for security applications. Then we have the SHA family. SHA-1, like MD5, was popular for years, but it's also broken now, meaning it's no longer collision resistant. The SHA-2 family, which includes SHA-224, SHA-256, SHA-384, and SHA-512, is currently trusted and widely used. And after that came SHA-3, which is a completely different design included in modern systems for added security. Now, to create message authentication codes, we usually use these secure hash functions along with a secret key. And that combination is called HMAC, which is short for hash based message authentication code. It ensures both data integrity and authenticity. In short, older hash functions like MD5 and SHA-1 are now outdated, and we always use SHA-2 or SHA-3 when building secure authentication mechanisms. So with that, we've come to the end of this video, and in the next lesson we'll be learning about secure socket layer or SSL. So thank you for joining in, and I'll see you next time.